So we're diving into this roller vibration scenario where we start with a force of 5,000 N and a time duration of
Yeah,
10 minutes, which converts to 600 seconds, right?
exactly. It's pretty straightforward when you think 10 minutes times 60 seconds per minute gives you that 600 seconds.
Yeah.
Simple math there.
And then we plug that into the vibration formula. Vibration, 0.02 times force times sin, 62.8 times time. So with F is 5,000 N, it's like 0.02 x 5,000 equals 100. And then we've got sin, 62.8 x 600.
Right. Making it vibration, Ryu, 100, multiplied by sin,
exactly.
37680. But then we hit that sign simplification step, which brings our angle back into a single cycle by doing a modulus with 2p. Yeah.
Sure is. So we get 37680 mod 2p, which lands roughly at 4.69 radians. And from there, sin 4.69 comes out to approximately 0.996.
Right.
So multiplying that by 100 gives us a vibration of about 99.6.
Exactly. And this value, 99.6, is just at that precise 10-minute mark, even though the actual vibration oscillates nicely between 100 and 100 continuously throughout the time period.
And here's an interesting point. You know, despite getting that neat 99.6 figure, it's tricky, really tricky, to deduce the roller's weight strictly from this vibration number, because the vibration depends on several factors beyond just weight.
Like the applied force, the frequency, remember that factor 62.8, and even the material properties where, the roller's design itself plays a major role. It's like trying to guess a cake recipe from just the taste.
Right, and to actually estimate the weight, you'd need additional data like the roller's dimensions, material density, and the precise compaction target, like the desired degree of soil compaction. Without those, it's pure speculation.
Now, switching gears here, let's talk about the volumetric void fraction, or VVF. That's basically the measure of empty space in soil, right?
Exactly, and when a roller passes over the same section, the VVF decreases, meaning the soil becomes more tightly packed. It's almost like, squeezing out all the air bit by bit.
And the graph we're looking at usually plots the number of passes on the x-axis and the VVF on the y-axis. So with each additional pass, especially under greater pressures, like 4F versus 1F, the VVF drops quicker, getting denser faster.
And what's pretty cool is that you often see two sets of data, one for the bottom of the soil layer and one for the mid-height. Typically, the bottom compacts more efficiently due to direct pressure.
However, I do have a slight critique here. While it makes sense that higher roller pressures yield lower VVF faster, it's not clear if the model fully accounts for variations in soil texture. Don't you think that might be an oversight?
Yeah, that's a fair point. Different soils might behave unpredictably even under the same pressure.
Right on.
One size might not fit all in these scenarios. Also, a key definition to nail down: one passage in the context here means a single unidirectional movement. So if the roller goes forward and then back over the area, that counts as two passes, not one.
Exactly. Each direction counts as its own pass, which is crucial when you're graphing the change in VVF with passage count. Every pass matters in achieving optimal compaction.
Yep. And these insights really underline that while the formula gives us a clear picture of vibration at a moment, getting the full engineering picture requires a lot more context and data. Layered and nuanced understanding is key here.
All in all, it's like a fascinating interplay of physics and engineering. Calculating vibrations one moment and deciphering soil compaction dynamics the next. It really highlights the complexity behind seemingly simple tasks.
Definitely, and it shows how every parameter, be it force, time, or even the number of passes, can significantly impact the end result.
Indeed.
It's all tied together in a beautiful, if sometimes messy, engineering puzzle.